All right. Next thing we're going to talk about is optics. Now, optics is the interaction of light with matter. And obviously this leads to telescopes, because the telescope was the best invention ever for astronomy. And it still is the most powerful tool that we have in astronomy to figure things out. So, we have to understand optics, and optics is interacting light and matter. And this is something that's been going back, and this went way back even into the 1400s. This was even before the Renaissance. They were using glass, and glass has been around for a long, long time, okay? And they were starting to use lenses, and they even had glasses that people could start wearing, even back to the 1400s. So the telescope wasn't invented until I remember 1609. So one of the things that people wonder is, why did it take so long to invent the telescope? Because it really wasn't that complicated of invention once you figured out lenses. But to talk about lenses, let's talk about how light works and how light interacts when it goes through something. So for example, you see this block, I can see you through it, right through it here. And you can see me, you should be able to see my eyes through the block. So what that means is these light waves that are traveling here go right through the substance and come out the other side. But does that mean they're not affected when they're going through it? Well, let's look at this and think about this here. So I'm going to put this block up here on our wall. This is the block. And I'm going to turn on these two light sources, which just make light rays, and I want them to be like parallel light rays. So we can just compare what happens to the light rays as they go through. In fact, I'm going to adjust the light so we can see a little bit better here. Let's do it like that. All right. So these light rays go right through the block. You can see them passing through the block and coming out the other side, pretty much unchanged. However, you might say, oh, so the block isn't doing anything. That's not true, because watch, all I have to do is this. If I rotate the block, notice it's shifting the light rays. The light rays that were up here, coming in, now have shifted down and came out. They're still parallel, but they got shifted. So something is happening as the light passes through the block. So even though it seems like the light just passes through, the light is interacting with that material. And what has been discovered is, when light goes through a different medium, as it changes medium, it changes speed. And so we change the speed of light. So what makes light bend or refract which is just a fancy word for saying bending of the light, is that light slows down through or I shouldn't say slows down because it depends on what kind of medium. Light changes speed as it changes mediums. So, what's happening over here, the light is going through the air, these parallel light rays, then they hit the block. When they hit the block, they slow down. But then when they come out the other side, they speed up again. And when that happens, it's going to make it bend if it's hit at an angle. Now, if it was straight on, they slow down and speed up. But you really don't notice any change because they're slowing down and speeding up in a straight line, so you can't see that change. So then the question is, okay, if it changes speed as it goes through this block, then if I don't have parallel side, which is what this rectangle has, I can actually bend the light to do what I want. And that's the idea of a lens. So here is a lens, and when we put our lens here, you notice that notice that I can't get the lens on up. There we go. Oh, so my lens will not stay in position here. I need to add another magnet here to help me out. And if if I have a lens like this, you see this one side is curved on the lens, one side is flat. The light hits it, and because it's curved, the light slows down and it's going to bend in. Essentially, you hit it when you hit it at an angle, that side's going to slow off a wave, it's going to slow faster than the other side, so it's going to make it turn. And this light gets focused here out at a point, and I'm not sure the parallel light rays are quite parallel there, but we'll do something like that. Notice that the light rays come together here. We call this a converging lens, or a converging lens because the light rays come together, or sometimes called a convex lens. Convex because the curve is this way instead of this way. It doesn't make a cave, it makes a vex. Well, I'm not sure what a vex is, but you get the idea. Alright, so this point here where the light rays come together is called the focal point. And this is what you're doing when you try to take a lens and you start a fire. So here I have my lens and I want to focus that light to a point. What I'm doing is I'm taking all the energy that's hitting the lens and I'm focusing down to a really tiny point. The tinier the point, the higher the energy density as that point. And that point can get very, very hot. And that's how you start a fire using the lens, is you focus the light to that point. So what you have to do is make sure that sun's rays are so far away, they're coming in parallel, that the object that you want to start the fire on is exactly the focal length away from the lens. Where the focal length is the distance between the center of the lens and the focal point. Now, we realize that light, when it hits the lens, it gets bent as it comes in and it gets bent as it goes out. So it really bends two places, but it's easier just to think of it being bent once in the center of the lens. All right, now look at this setup here. I have the parallel side on this side and I have a curve on this side. Will the focal point change position if I flip the lens over? Well, let's see. So if I turn the lens around, so the parallel light is coming in there. All right, I adjust it a tiny bit there. Then, no, the focal point should be the same distance. The focal length is still the same. Light doesn't care. Light doesn't care whether it's going through this way or this way. It's going to react the same as it goes through that lens. Okay? And the greater the curvature, then the shorter the focal length. So if I have one like this, where I have a very sharp curve, okay, and I replace my lens with this, the focal point should be significantly shorter in this case. So in this case, the focal point is very close to the lens. The focal length would only be this far, and the focal point would be here. Okay? So that would make it very much shorter. So the bigger the curve, the shorter the focal length. And whenever you buy a lens, the key to the lens, or the key properties to our lens, is its size, its diameter, and its focal length, where it focuses at. And that depends on how much curve it has, whether it's curved on both sides, what they call a double convex, and what it's made of. Different materials bend light differently, or what that means is different materials slow down the speed of light more than others. And the one that slows it down the most, you might guess it, is a diamond. Diamonds have what we call the highest index of refraction, which means their ratio of the speed of light in the substance compared to the speed of light in air is very high. Which is why diamonds, when they're cut right, light comes in and gets bent around and comes back out, and that's what makes them sparkle. Which is why people like them. That's why when you buy a cheap piece of glass, it doesn't look like a diamond. And that's how jewelers and stuff will test to see if you have fake jewelry or not, is they'll just shoot light through it and see how it bends. You can't fake that property, it's a physics property. Alright, so refracting of light is caused by the bending of light as it goes through an object. Alright, so how do we make a telescope? Well, the first thing we do is we take a simple double convex lens. And I'm going to show you how. I'm going to turn this off for a minute. We'll come back to this here. how to use a convex lens. Turn the light on real quick here. To make a telescope, but two convex lenses actually. We have to have two lenses always to make a telescope. All right, so when you have a convex lens, light gets bent to the focal point. So we just learned, and here's my convex lens. Remember, convex is bent like this. Okay? What we're going to care about is the middle of the lens. That's what we're going to bend the light rays. And we notice that here, this is what was called our axis. Should be a straight line, perpendicular to the lens. All right, and then there's a point out here, depending on the curvature of it and what it's made of, where the focal point is. And there's an equal focal point on the opposite side. So we have a focal point there. Now there's something tricky about lenses that if you have a lens in your house, go try this, okay? Everybody knows that you can take the lens and it just magnifies it. So you can magnify your fingerprint or whatever you're looking at. And people use it to read, you know, something's close, especially old people when their vision gets bad. A magnifying glass really helps to read things. And so you can see that. But most people don't realize if you hold your hand out very far, depending on the focal length of the lens, and you look through it usually with one eye, what you see is that the image in there is actually flipped over. It's made upside down. And you're like, oh, how can the same lens make this right side up and magnified, but when I hold it way out here, it flips it over upside down? Okay, the lens is still doing exactly the same thing. Lens doesn't know where the object's coming from. It's just bending light. So let's look at this. We have two cases. We're going to call this case 1.